Okay. Good evening, everyone. We are going to be recapping organic chemistry. And we begin by looking on a summary of the introduction as well as so when I look on the summary of the introduction, so we're going to define some terms. So homologous series is a group of organic compound and each member has the same functional group and the same general formula, right? Characteristics of homologous series, again, you are to recall any 4 characteristics. So each member differ from next. You must use the word next preceding our previous member by CH2. So the word next can be substituted with next, preceding, or successive member. They have similar chemical properties or they can be prepared the same way. CXC accepts number 2 as 1. So you can't say similar chemical properties and you give another point can be prepared the same way. CXC considers that to be 1. They have the same general formula, same functional group. As the number of carbon increase, there's a change in physical property. One such property is boiling point. Boiling point increases as the number of carbon increases. So I want to continue defining terms. A functional group is atom or group of atoms in an organic molecule, which determines the chemical property, right? Hydrocarbons, compound with only carbon and hydrogen atom. Homologous series, we have alkane, functional group, carbon-carbon single bond, general formula CnH2n plus 2. We have alkene. Alkene have carbon-carbon double bond, general formula CnH2n. Alkanol or alcohol, they have the hydroxy, which is the OH. The general formula is CnH2n plus 1 OH. Then we have alkanoic acid. Alkanoic acid has the general formula carboxyl, which is represented by COOH, and the general formula is CnH2n plus 1 COOH. We have ester. The functional group is C double bond O. The difference between the alkanoic acid and the ester is that the alkanoic acid must have a H. So if you're circling the functional group for that, you must circle COOH. For the ester, it's COO, and the next part of the compound will have a C, but the functional group is actually just the COO, right? So you need to be able to distinguish between that. Now, what are isomers? Isomers are molecules or compounds with the same molecular formula, but different structural formula. Students tend to mix up isotopes, isomers, allotropes. So although it's organic chemistry, I will discuss each of them now. Isomers, molecule with the same molecular formula, different structural formula. Allotropes, different physical form of the same element. Example, carbon has 2 allotropes, diamond and graphite. Isotopes are atoms of the same element. They have the same number of proton, but different number of neutron. Do not mistake them. Now we need to memorize, and we see girls, we didn't do isomers of C4H8. So now is a very important time to make a note of this. So isomers of C5H12 are pentane, 2-methyl-butane, 2,2-dimethyl propane. You should be able to draw all of these. Isomers of C4H8 are butane or but1-ene, 2-methyl-propane, 2-methyl-propane or and but2-ene, as well as we have, which one don't I have here? Those who come here on Sunday are supposed to know this. Cyclobutane is also the 4th isomer. So isomers of C4H10 are butane and 2-methyl propane. Reactions of acid. We consider reactions of alkane, We consider alkanes to be a saturated hydrocarbon, and it is a saturated hydrocarbon because it only consists of carbon-carbon, single bond. Alkane can undergo combustion reaction. In combustion reaction, alkane reacts with oxygen. Where is this question mark? It's supposed to be an arrow. I don't know why it present like that. I'm not gonna fix all of them, but these are supposed to be arrows. So alkane and oxygen burns to give carbon dioxide and water vapor. So alkanes are used as fuel because they burn. When they burn, they produce a clean blue flame. The reaction produces a large amount of energy, and lastly, they are easily stored and transported. At the time of making this handout, they only really test for these two alkanes and what they're used for. However, we know that we're supposed to know all the first six. So butane is a refrigerant, right? So butane is used as a refrigerant. It's also used as a lighter fuel, and it is used as fuel in portable stoves. Then we have propane. Propane is bottled gas for domestic purposes, and it's used for fuel in cutting and welding. I'm not supposed to memorize the rest of them. So hexane, just because hexane was on last year paper, used as a solvent, can make glue. All right. I remember rest of them. Me not do exam, so I don't need to know pentane, methane, and so if somebody have them, I'll write them here. Anybody have pentane or remember methane? Remember goods now, remember these things, because me not sweat. Anybody know the use of methane?
Miss, I have that methane is used for natural gas for cooking and those things, and raw materials in the chemical industry for production of various organic compounds.
Anytime you use cooking, I'm always putting the word fuel there because I'm conscious that that's what it's used for. Anybody have anything for pentane? Octane is gasoline, petrol, in cars. Nobody not have pentane, nobody not have ethane. We're going to all of these and tell me if you study them. See, I don't study them, I know, I'm not the exam. So when you're balancing the burning reaction, we always balance the carbon first, followed by the hydrogen, and lastly the oxygen. Cracking. Cracking is a process by breaking long-chain hydrocarbon into smaller, more useful fraction. Cracking is important because it produces very useful alkane, such as petroleum, and it also produces smaller, more reactive alkene, which is used as starting material in the petrochemical industry. Anything will come from petroleum products, we call the petrochemical industry. But generally, alkenes are used to make polymers. So for example, propene is used to make polypropene. Ethene is used to make polyethene. So we have two types of cracking. We have thermal cracking. In thermal cracking, we use high temperatures of about 700 degrees Celsius and pressure up to 70 atm to break a long chain hydrocarbon into smaller, more useful hydrocarbon. We have catalytic cracking, used as a catalyst, and temperatures of about 500 degrees Celsius and low pressure to break long chain hydrocarbon into smaller, more useful hydrocarbon. So generally what you want to make sure is that your products your 2 products or 3 products that are formed, they add up to the number of carbon and hydrogen in your starting material. Then we have substitution halogenation. In substitution halogenation, an alkane reacts with a halogen to form haloalkane and a hydrogen halide. The condition for this reaction is UV light. Now, in a substitution reaction, one hydrogen atom, get less and a chlorine is increased, or a halogen increases while the hydrogen goes down. So we start with C4. So we start with methane. Methane reacts with chlorine, and when it produces CH3, so it's 1 less hydrogen, 1 chlorine. So it's CH3Cl, which is chloromethane, and HCl. Then we start with chloromethane. Oh God. Where was I? Let me fix this. So the Cl must be bigger. Plus Cl2 produces CH3. So 1 hydrogen gets less. So we started with 3. Now we have 2 hydrogen. And we gain a chlorine, so it's Cl2. And the name of this compound is dichloromethane, and we form HCl. Then we have C2H4. So plus chlorine. We start with 2 hydrogen, so 1 hydrogen is gonna decrease, so we end with CHCl3 and HCl. Then we start with CHCl3 and add it with a new chlorine. This is so wrong. No, hold on. And then we end up with carbon tetrachloride. So what happens when I copy and paste? I'm gonna post it on a different WhatsApp group that we have started. All right. So the overall equation is we have 1 methane molecule reacting with 4 chlorine molecules. So only unless they ask you to form carbon tetrachloride are you going to use this equation. Any other reaction, they'll ask you for a series of equations. They'll tell you that they want 1 equation, or they'll say using equations. So we have C4, so methane CH4 gas plus 4 chlorine produces CCl4, which is carbon tetrachloride, and 4 HCl. Now, what can be merged with this is a little inorganic chemistry, where they're asking you testing for HCl, how you test for HCl. So you'd place a glass rod dipped in concentrated ammonia. If white fumes is produced, then HCl gas is produced. You are also required. You can also be asked to write the equation for this reaction. And in writing this equation, we start with HCl gas so we have HCl gas forming ammonium chloride Why we can't use the iPad, yeah. Forming ammonium chloride, which is NH4Cl. So that's it for alkanes. Also, on the alkane, you need to be able to distinguish from an alkane to an alkene. So, bromine liquid is red or red brown. So when we add an alkane to bromine liquid without any UV light, bromine liquid will remain red or red brown. If we add it to an alkene, it's gonna turn from red brown or red to colorless. Bromine solution is orange, so orange bromine water is going to remain orange, right? So in an alkane, whereas in a alkene, orange bromine water will turn colorless. Bromine liquid, in UV light, bromine red color is slowly going to change from to colorless, For the alkene, bromine is going to rapidly change from red to colorless, or you can use red brown, whichever one. For acidified potassium permanganate, in alkane, acidified potassium dichromate is going to remain purple, whereas in an alkene, it turns from purple to colorless. Now we're on to the next homologous series, which is alkene. Alkene has the general formula CnH2n, so the number of hydrogen is double the amount of carbon. The functional group is carbon-carbon double bond, right? So we have it is considered unsaturated because of the presence of carbon-carbon double bond. So any molecule which has the presence of a carbon-carbon double bond, we refer to that molecule as unsaturated. No, alkenes is extremely reactive, right? And it undergoes reactions such as hydrogenation. In hydrogenation, hydrogen gas reacts with an alkene to form a alkane. The condition for the reaction is nickel catalyst, 150 degrees Celsius and 5 atmosphere. We have hydration. Hydration is the reaction between alkene, and water. When in hydration, the double bond is broken and to one carbon in the double bond, we're adding H and OH, so we form a alkanol or a alcohol. The condition for hydration reaction is concentrated phosphoric acid, 300 degrees Celsius and 60 to 70 atmospheres. We have addition halogenation. So we need to understand that there are two types of halogenation. The halogenation that an alkene undergoes is referred to alkane undergoes is referred to as a substitution, and the one that the alkene undergoes is referred to as an addition halogenation. So in additional halogenation, alkane reacts with a halogen molecule to form a dihaloalkane. We need no condition for this reaction. Now, in oxidation, we react an alkene with an oxidizing agent, such as, which is acidified potassium dichromate, and it will form a diol. So to the double bond, we're adding 2OH, so we get a diol or a dialcohol. So now we're on to our next series, which is our alkanol or alcohol. So we need to understand fermentation. So fermentation is the process by which complex carbohydrate breaks down to glucose, or instead of complex carbohydrate, you may use sugar. It's the process by which complex carbohydrate breaks down to form glucose, and then glucose is broken down to ethanol and carbon dioxide by the anaerobic respiration of yeast. Also, the reaction is catalyzed. CSEC, so they're looking for that term. So let me add it. It's catalyzed by the zymase in the yeast. So if they ask you for 2 equations, we did only one yesterday, girls, but there's one particular past paper question. They ask it one time in CAPE and one time in CSEC, where they're saying like, listen, if they want 2 equations, you start off with sucrose first. Sucrose is C12H22O11, and you add water. That's going to produce 2 glucose molecules. Then the second equation is to react a glucose molecule with add the yeast to it, and then you're going to convert the glucose molecule to 2 ethanol and 2 carbon dioxide gas. The mark scheme says that they are looking for temperature range anywhere between 25 degrees Celsius and 37 degrees Celsius. You need a low pH, which is generally somewhere between 4 to 6. And the next condition is zymase. We do not use temperatures above 37 degrees Celsius. Temperatures, high temperature denatures and kill the enzymes. All right, so the ethanol that is formed from fermentation process, this ethanol that is formed from the fermentation process, if we leave it out to oxygen gas, it can be converted to ethanoic acid, which is a bitter and sour mixture. Just using these terms because these are terms that they use in the examination. All right, so if ethanol is left out, so for example, if you have a beer and you leave the beer out, oxygen is exposed to it. The oxygen can react with the ethanol to produce ethanoic acid. Another name for ethanoic acid is acetic acid. Sorry. Ethanol can also be prepared by the hydration of alkene, which we discussed just now. Ethanol reaction. The fermented mixture can be separated using. So the fermented mixture can be separated using fractional distillation. You should be able to draw and make sure you're able to label this diagram. So if you can draw this is really just a heat source. You can just draw around, put a heat source. So in there you have a mixture of ethanol and water, or you put the fermented mixture there. So this is in a round bottom flask. Your round bottom flask is then attached to a fractionating column. The fractionating column is what is going to separate the ethanol and water, because both of these, ethanol and whatever solution you have there, have a similar boiling point. So what is happening is that when you heat them, both the mixtures are going to evaporate. So the fractionating column is what separates the mixture. Generally, there's a series of condensation and evaporation taking place. Every time we have condensation in the fractionating column, the liquid with the higher boiling point, it falls to the bottom. So at the end of the fractionating column, we have a liquid, which would be pure ethanol. We have the thermometer. The bulb of the thermometer must be near to where the vapors are entering the condenser. So here we have a condenser, or it's called a lean back condenser. You need to put water in. Water in is at the bottom. Water goes in at the bottom because we want to make sure the bottom is coldest, so that the water vapor, so that all the vapors are converted to liquid. So water goes in at the bottom and it enters out through the top. want to make sure the bottom is coalesced so that all the vapors are properly condensed, and then we collect the distillate in a evaporating dish. What we also need to remember for alkanol is that alkanols are polar molecule, and they are polar because the oxygen is more electronegative than the hydrogen in the hydroxy group. So oxygen is a bully. It pulls the electron towards itself and away from hydrogen. This results in the hydrogen becoming slightly positively charged and the oxygen becoming a slightly negative charge. So the polarity has to do with slight charges. Water is also polar for the same reason. The oxygen in the water pulls away the shared pair of electrons from the hydrogen, making the oxygen slightly negatively charged, and the hydrogen slightly, making the oxygen slightly negative and the hydrogen slightly positive. So any molecule with that shows the polarity. Then ethanol is less volatile. Volatility means your ability to turn to vapor. So alkanols do not readily vaporize like your alkanes, right? So they don't have a low boiling point. Their boiling point is going to be higher. So you'll find that methane have a lower boiling point than methanol. Reason being, because of the polarity of the alkanol, it allows the alkanol molecules to form strong hydrogen bonds within itself. So within the molecules, right, they can form hydrogen bonds, making them difficult to break. So they have a high melting point compared to their alkanes. What is wrong with these dogs? Then for our reactions, we have, don't know the document yesterday. For reactions of alkanols, what we have is combustion. So like every other organic compounds, they burn in oxygen to produce carbon dioxide and water vapor. So ethanol is used as a fuel as itself, or it is mixed with gasoline. The reason being is ethanol burns. When it burns, it produces less carbon dioxide compared to gasoline, and ethanol is a renewable resource. Ethanol can react with sodium. You need to know this reaction as per your syllabus. So I would sort it. 2 ethanol plus 2 sodium form 2 sodium ethoxide. To form the ethoxide, all we're doing is replacing the hydrogen in the ethanol with a sodium. And to balance this equation, we're going to put 2 in front of everything. Then we have oxidation. In oxidation, ethanol is converted to potassium permanganate or potassium dichromate. Ethanol can be oxidized using acidified potassium permanganate or potassium dichromate. In the so when it's oxidized, it forms ethanoic acid. So it's a similar reaction to when it reacts with oxygen here, oxygen in the air, but we can use the oxidizing agents to do that. In the oxidizing agents, we need acid. We use the oxidizing agent and heat, not 170 degrees Celsius. This should be heat, and we produce the acid and the water. Please note, your syllabus says that it does not want this equation, so I'm letting you know, but you must know the observation. So if we use ethanol and we boil ethanol in acidified potassium dichromate, we will observe that dichromate moves from purple to colorless. If we use acidified potassium, let me feel like I said dichromate a while ago. Let me say that again. So if we use permanganate, permanganate turns from purple to colorless. If we're using acidified potassium dichromate, it turns from orange to green. So in this scenario, if this was a redox question, we know that acidified potassium permanganate and acidified potassium dichromate are reducing agent. So that would mean alcohols are, so acidified potassium permanganate are oxidizing agents, sorry. So they're oxidizing agents, and we use oxidizing agent to test for reducing agent. So this would make us know that alcohol or ethanol is a reducing agent. So they can merge them. They can get very creative in the exam. That's not our problem. Our problem is just to understand the chemistry. Breathalyzer test hasn't come in a very long time, but in the breathalyzer test, somebody who is suspected to have consumed too much alcohol, right? You will, the police will ask the person to blow on crystals of acidified potassium dichromate. And if they have alcohol present in their lungs, when they exhale over these crystals, the crystals are going to turn from orange to green. Then we have dehydration, which is the opposite of hydration. So in hydration, an alkene reacts with water to form an alkanol. So now in dehydration, an alkanol will form a alkene and water. The condition for dehydration is concentrated phosphoric acid, 170 degrees Celsius. So hydroxyl, the OH group is an hydrogens. They're removed from adjacent carbons and we form the double bond and the water. So you need to know the condition for this reaction. So that was a lot in another half hour. Looking for a file. All right. So now we are at, I'll look for the file in a minute. Now we're at alkanoic acid. For some persons, this is going to be new. So if you were here yesterday, this is going to be new because we didn't really go in depth yesterday in alkanoic acid. So your carboxylic acid or your alkanoic acid, they react like regular acid. So I'm going to do some reactions. So again, it is formed. So if you want to form a alkanoic acid, they are formed from the oxidation. They are formed from the oxidation of alkanol using acidified potassium dichromate, or this is permanganate or acidified dichromate, C2, K2Cr2O7, right? So that's how we prepared them. So we need to know their reactions. We have done esterification in depth. So we're going to be looking on the other reactions. So using ethanol. So ethanoic acid, sorry, can react with metal. And when they react with metal, they form salt and hydrogen gas. Or they can react with bases. Bases are metal oxide or metal hydroxide. And when you do that, they form salt and water. They can also react with carbonate. And when we do carbonate, we mean metal carbonate or metal hydrogen carbonate. When they do that, they form salt, water, and CO2 gas. Now, what we need to remember is that ethanoic acid has a lot of acid, but the acid which forms the H plus ion when dissolved in water. So acids are substances which dissolve in water to form H plus ions as the only positive ions. So this hydrogen is the acidic hydrogen. So this is the acidic hydrogen. So this is the only hydrogen that is replaced when an acid reacts with a metal or a base or a carbonate. This is the H that is replaced. What we also need to know is that the ethanoate ion is CH3COO minus. So it has only one negative charge. So if we form a metal, if we form a compound like calcium ethanoate, calcium has a 2+ charge. The ethanoate ion is H3COO minus. But in the ethanoate ion, in the salt, this comes first. So if we're forming calcium ethanoate, this is the formula. Calcium is 2+. So to get rid of the 2+ charge on the calcium, we're going to need 2 ethanoate ions. So it's going to be CH3COO close bracket 2 calcium. So your organic salts, you put the anion first, or the alkanoate ion first, and then you put the metal. So if the metal is 1+, for example, if we're forming sodium ethanoate, because the sodium ion is 1+, it's going to be CH3COO minus, and then we have the Na+, so the formula is CH3COO Na. So now we're going to be looking on some reactions. So CH3COOH, if we react that with sodium, we're going to form salt and hydrogen gas. The salt would be CH3COO Na, right? Because it's only one hydrogen replaced and we form hydrogen gas, which is diatomic. To balance this equation, we're going to put a 2 here, a 2 here, and a 2 here. So that's how we're balancing the equation. To get H2, we would need 2 acid molecules, and then we would get 2 salts. And if we get 2 salt, we would also need 2 sodium. Now, this is another one from a past paper where they're asking you to react ethanoic acid with a base. And in the past paper, they are using magnesium oxide. Now, magnesium is also 2+ like calcium. So the formula would be CH3COO close bracket 2 Mg. So this is the salt, CH3COO, and then we put Mg right here, and we get the water. To balance this, what do you mean a bracket it? Because we're using 2 ethanoate ions, we would need 2 ethanoic acid, right? And then this 2 with this 2H will give us the 2H in the water. 1O from the magnesium give us 1O from the water. So our equation is balanced. So to balance this reaction, we're only putting 2 in front of the ethanoic acid. So here I've done one with a metal, one with a base. So we need to do one with a carbonate. So we're going to use calcium carbonate. Ethanoic acid plus calcium carbonate. I mean, I have no state symbol. Calcium carbonate. Somebody needs to mute. We're going to form calcium ethanoate. So CH3COO close bracket 2 calcium plus carbon dioxide and water. So those are the reactions that we are to know. We're also to discuss the polarity of the acid. So acids generally have COOH. So because of the presence of the OH, it is going to be, thank you. So because of the presence of the OH, it is also going to be a bully. And pull the shared pair of electron towards itself. So your acids are polar, but they are more polar than your alkanal, and they react better with metals. So remember, ethanol reacts with sodium to form sodium alkoxide or ethoxide. Now, your acids react better with metals because they lose the H plus ion more readily. So your acids and your alkanals are both polar. So both of them are polar, but the one which is more polar is the acid. Your alkanals react with metal, but the one which better reacts with the metal are going to be your acids, because your acid reacts better with metal because they lose the H plus ions more readily than alkanal or alcohol. And again, we're only covering it and we're saying it because it does answer a past paper question. So anything when we revise, it come in a past paper question that we're going to do today that we need to be able to look on. So our last reactions now are esterification. So in esterification, we react a alkanoic acid or a carboxylic acid with a alcohol or a alkanal, and we produce ester and water. I'm lazy. So in the ester reaction, what is happening is that the COOH from the alkanoic acid is going to, so the carboxyl, which is the COOH, is going to lose the OH, and we are going to remove the H from the alcohol. So this is what is happening. Start off with an acid. This is any acid, any alcohol. We put the OH part of the alcohol first, and we are going to remove the water. When we remove the water, the acid will have the RCOOH. So the RCOOH is going to come from our acid, right? And the OR is coming from our alkanal. And remember, it's a condensation reaction, which is catalyzed by concentrated hydrochloric acid, concentrated sulfuric acid and heat. In some cases, you may see HCl. So it's using concentrated sulfuric acid and heat to catalyze the reaction. So here we have an example where we have ethanoic acid and methanol. ethanoic acid has 2 carbons. So when we draw it out from the carboxyl, we circle, we are removing the OH, and from the OH, from the hydroxy, we remove a H, so we form an ester and water. Now, our ester is named alkyl alkanoate, where the first alkyl comes from the number of carbon in the alkanol. So in this case, I'm reacting methanol. So my name of my ester is methyl, and then it's called alkanoate, where the next alk is referring to the number of carbon, using the prefix for the number of carbon in the acid. So the number of carbon in the acid is 2, so it's ethanoic acid. So the entire ester name is called methyl ethanoate. Here we have another example where we're using propanoic acid and ethanol. In propanoic acid, we remove the OH from the carboxyl, and remove H from the hydroxyl to form the water. So what we're left with is the ethyl propanoate, which is the ester, because the alcohol, is ethanol. So the first name comes from the alcohol, so it's ethyl. The last name comes from the acid, so it's propanoic acid. So the name of the ester is ethyl propanoate. So this is what ethyl propanoates look like. I remove my OH and my H, and I form my ester and my water. Now, we're going to be looking on reactions of ester. So an ester is identified by the C double bond O. So the functional group for the ester is C double bond O, or COO. Your C double bond O, your C double bond O. So when the ester reacts, this bond between the carbon and the single one oxygen is broken. So we're going to break this bond. In acid hydrolysis, we boil the ester in acid, like dilute hydrochloric acid or dilute sulfuric acid, to get back the water. So in acid hydrolysis, what we're doing is we are adding the OH is added back to the acid, and H is added back to the alcohol. So what we're forming back is we're forming back the ester and the alcohol that we started with. So here is an ester. We have 1, 2 carbon in there from the alcohol. So this is ethyl. The acid have 1, 2 carbon, so it's ethyl ethanoate. Again, when an ester break, we're breaking the bond between the carbon and the single bond oxygen. So here we are breaking this bond. When we break the bond to the portion that was the acid, which is the part, so the part with the acid has the carbon double bond O. So that portion, we're adding back OH. So notice I split the molecule right there, and I added back OH there. This part with just the O is, so this part with just the O came from the alcohol. So when I split the molecule here, I am adding back H to the alcohol part. So that is acid hydrolysis. The molecule split, the ester molecule split between the carbon and the single bond oxygen. When my molecule split to the acid, which is the part with the C double bond O, I will add back the OH, and to the alcohol, I'll add back the H. So I'm forming whatever alcohol and whatever acid that form my ester. Now we have alkaline hydrolysis. Again, the molecule is going to split between the carbon and oxygen single bond. When the molecule splits there to the acid, we're going to add ONA or OK, depending on the alkali that we are using. And to the alcohol, we're going to have H. So here we have 1, 2, 3, 4 carbons from the alcohol. That's butyl. 1, 2 from the acid. So this is butyl ethanoate, and I'm reacting butyl ethanoate with sodium hydroxide. When I react to that, the molecule is breaking between the carbon and the oxygen right here. So I'm splitting the molecule here. When the molecule split to the acid part, which is this part, I'm going to be adding ONA, which is what I have here. I don't draw a single bond because ONA is a ionic molecule, so that part of it doesn't form a covalent bond, so I don't use a dash. So I put a O minus and an Na positive. And then to the alcohol part, I'm adding back the H. So here I am seeing, this is what I added. When I split the molecule. So when I split the molecule here to this part, because it's NaOH, I'm adding O minus, Na plus, and I am adding H back to the alcohol. So I'm forming a salt, and I am forming my alcohol. Now here I have a fat molecule, which is just a large ester. Me nah do no polymerization. Nah do it. CH2. I'm a pen change. So in this molecule, I am seeing 3 functional groups, and the 3 functional groups are the same. I am seeing ester here, and ester here, and an ester here. This is a fat molecule or an oil molecule. And I am going to be reacting this molecule with 3 NaOH. So again, where the ester is, where I find my ester linkage, so where my ester linkage are, the molecule is gonna split there. So right here, my molecule will split. So if I'm reacting it with NaOH class, when the molecules split right here, the part with the acid, which is the C double bond O, so I will have R, C double bond O, the part with the acid, I'm going to add O, Na. So it's 3 sodium hydroxide. So all of these are going to form RONA. So it's 3 RONA I'm going to form, and this is going to be my soap. Now, the other parts of the molecule, I want to rub out this, not sure how it's going to work. All right, let me draw it back to get the other parts of the product. So when the molecules split here, we're only focusing on what else is forming. So when the molecules split right here, we already figure out what's happening to the ester part, to the acid part of the ester. So we're going to be looking on the alcohol part. So the alcohol part, each of them is going to get a H right there. So the molecule that forms is CH2OH, CHOH, and CH2OH. This molecule is called a glycerol molecule, and it is a byproduct from the saponification process. So saponification is boiling fats and oil into a base called lye, which is sodium hydroxide. So you're boiling it in sodium hydroxide and you produce soap, right? Now soap does not lather well in hard water. If you put soap in hard water, it's going to form scum. Scum is this great thing that you see, say if you put in your uniform and you're rubbing it with cake soap and you put it in the water, you're going to realize that you get some gray film instead of sun. That's what we call scum. Now you should be able to distinguish between soap and soapless detergent. No, soaps are biodegradable, while soapless detergents are non-biodegradable. Soaps are produced from renewable resources, like your fats and oil, you can always get them the back. Whereas your detergents or your soapless soaps are made from petroleum products, which again, we know that those are non-renewable, right? We also have soaps are difficult to lather in hard water. They form scum. Your soapless detergent lather easily in hard water and they form sod, not scum. Then your soaps have no sulfates and phosphates, whereas your soapless detergent contains phosphates and sulfate. All right, this is me saying, I don't know, no polymer, but let's go. We have two types of polymerization. So polymerization is the process by which we form a macromolecule. So a polymer is a macromolecule formed when 50 or more monomer units are linked together. We have two types of polymerization. We have addition polymerization. The monomer units are linked together by the breaking of the double bond present in the monomer units, for example, your alkanes. So here we have, so in additional polymerization, the double bond opens up and is converted to single bond and the monomers are linked together. So here we have polyethylene, the monomer for polyethylene. Polyethylene is used to make plastic bag, cling wraps, diaper, barrier fluids, and the monomer is ethene. So the one monomer unit here, this is going to, the double bond here is going to open up to form a single bond. So this is where we have one monomer unit. Then we're linking three monomer units together. So this is really a trimer, using it to show the partial structure of the polymer. So the double bond opens up and you're just linking the three monomer units together. Here we have Teflon. Teflon is the it makes the adhesive, the non-stick component in frying pan, and it do some other stuff when we can't remember right now. You need to know the uses of each polymer. Sorry. So the monomer unit is tetrafluoroethane. Again, the tetrafluoroethane molecule is going to open up. So this double bond here converted to single bond, and we're repeating the monomer unit 3 times. Then we have polypropylene, used to make some plastic containers, cards, and some crates and some other stuff. The monomer unit is propene. So the double bond here is going to open up for us to have a single bond. Banana space to dry, but this is what it would look like. So that's one monomer unit. I'm gonna draw another one. And then you draw a third one, depending on what the question asks. Here we have polyvinyl chloride, aka PCV. This is used to make insulation for wires. In the home, you have wire insulation, pipe insulation. It's used to make pipe. Them something the gutters and them something that we use PVC for them. So again, the monomer is chloroethene. The monomer units open up. And then you repeat it by the number of times they ask you to repeat it in the question. So again, for each polymer, you need to know what they're used for. This is condensation polymerization. In condensation polymerization, the molecules, the monomers, oh, no, this one not it. Oh, up here, so we're saying the monomers in additional polymerization, they are linked together by an alkane bond. So the linkage in addition polymerization is the alkane linkage. Here we have condensation polymerization. Condensation polymerization, the monomers are linked together by the elimination of a small molecule, example, water. We have two types of polymerized we have natural polymers, which are starch or polysaccharide. Your monomer unit is a glucose, which is represented by a dialcohol or a diol. So that's your glucose. So basically what we're doing is we're moving water. Whenever we eliminate water, we are eliminating H and OH. So here we have two monomer units, right? And from here, we're gonna take out our water. And if another monomer was over here, we'd take out OH from over here. And another monomer was to the right of this, we would take out a H. So this is the partial structure of the polymer. So when we take out the H's and the OH, we're left with XO, XO. And the link, what's linking each X to each other is a O. So it's a O single bond O, and we call this an ether linkage or a saccharide linkage. We have protein, which is a natural polypeptide. The monomer unit is going to be your amino acid. Your amino acid has two functional groups, the amine functional group right here and the acid functional group. So from the amine functional group, we're going to take off a H. So here we have an amine, we want to take off water. So we take off the H from there. We're going to take off OH from the acid. So H and OH, we remove them, we form our water. Now, if another monomer was over there, we would take off the OH. If another monomer was over here, we would take off the H. So what we're left with is this. And the monomers units are linked together by C double bond O, NH, and or NHC double bond O. This is referred to as the peptide linkage or the amide linkage, right? Now, protein is needed for the growth and repairs of cell. It makes hormone and enzyme in the body. We have man-made polymer, which is going to be your why not there so your polyester. An example of polyester is terylene. I think that's how it's spelled. You cannot spell. I can't write. This is how it's spelled. So your monomer unit is your diacid and dialcohol. say diacid, C-double-bond-O, OH. Something in the middle, I don't care what it is. Then your dialcohol. So we're moving water. We're going to take the OH from the acid and the H from the alcohol. So I'm going to circle this. If another ester was over here, I'd also take the OH from here and the H from here to form another water. So this is how the partial polymer looks. C-double-bond-O, box, C-double-bond-O. Then I have a O, X, O. So what's linking a box to a X is this. And this is called the ester linkage. Polyethylene is used to make fabrics. It used to make robes. Different types of fabric, different types of material. So it's used to make upholstery as well. Like covering for your settee, used to make a uniform material. So the ester linkage can look like this, or it can look like this. It's still the ester linkage, and that's what we form in polyester. The last one we have is, we have another polypeptide, which is going to be nylon this time. And nylon is made from the monomer units. Diacid. And the diamine. The diamine has two amine, something in the middle, which I don't care what it is. So to form my ester, I'm going to remove OH from my acid, H from my amine. If another ester was here, if another monomer was here, I'd remove the OH from here. If another monomer was here, I'd remove the H there. So this is partial structure nylon, where I have C-double-bond-O. Oh. C-double-bond-O. And then from the amine, I'm going to have NH, X, NH. So what's linking my molecule together, my box and my triangle, is this. C-double-bond-O, NH, which is my amide linkage, or my peptide linkage. Nylon is used to make fabrics, fish line, fish nets. So it can look like this or this. It's still the same linkage because it's the same bonds. All right, so that is organic chemistry in an hour and about 15 minutes. We need a break. So